In this video I'm going to be looking at the solution to question 7 of the January 2011 Edexcel M1 paper. The topics covered in the question are connected particles and also kinematics. It's quite an involved question this, and the question starts off by telling us we have two particles A and B of masses 7 kilograms and 3 kilograms attached to the ends of a light inextensible string. It says the B is held at rest on a fixed plane, and it's a rough plane inclined at an angle theta to the horizontal. Told that tan theta is equal to 5/12. The string passes over a smooth pulley at P, and the particle A hangs freely below P. So all of this is shown in figure 4. The coefficient of friction between B and the plane is 2/3. It says the particles are released from rest with the string taut and B moves up the plane. Find the magnitude of the tension, find the magnitude of the acceleration of B immediately after release. Now that's the first part of the question. Once we've got the acceleration, the question goes on to say, find the speed of B when it has moved 1 meter up the plane, and then says at that point the string breaks. So given that the subsequent motion of B does not reach P, so it's going to stay on the plane, find the time between the instant when the string breaks and when B comes instantaneously to rest. Well, the first part of the question then is one about connected particles. Although quite an involved one here, because as well as just the particles being connected, one of them is on a slope, and also that slope involves friction. So I've put the information onto the diagram, which I would always advise you to do as well. And in there what we're going to do is, once we've done that, a standard sort of procedure for connected particles is to write down Newton's laws, F equals to ma, for each of the particles in turn. So for A, first of all, and if I take the forces acting downwards for A, then we have that 7g minus t must be its mass, which is 7, multiplied by the acceleration. For particle B, I'm going to look at the forces acting up the plane. So there we have got T, the tension in the string, and then acting down the plane. We're told that B moves up the plane, so therefore the frictional force is acting down. And then also we have the component of the weight. Now if I put that onto the diagram, theta is in here, and the component of the weight is going to be 3g sine theta, so minus 3g sine theta. So those are the forces, and they will be equal to the mass 3 multiplied by the acceleration. We're told that F is, we know that F is equal to mu r. And so resolving now perpendicular to the plane, so if that's the plane, we're resolving away from the plane, we can see that r is equal to 3g cosine theta. And with a value of mu equal to 2/3, this means that F must be equal to 2g cosine theta. So putting that into the second equation, I have that T, and then we've got in total minus F, which is 2g cosine theta, and 3g sine theta is equal to 3a. But we need to work out the values of cosine theta and sine theta. The question tells us that tan theta is equal to 5 over 12. Now this is a way of giving you sine and cosine without you having to do a great deal of work, particularly with a calculator. So if tan theta is 5 over 12, this is a 5, 12, 13 triangle, so you probably know that the hypotenuse there is of length 13. So the cosine of theta is 12 over 13, and the sine of theta is 5 over 13. So this bracket becomes minus 2g multiplied by 12 over 13 plus 3g multiplied by 5 over 13. And if you calculate that, we've got 24 over 13 and 15 over 13, so 39 over 13. So in fact, that big bracket there turns out to be simply 3g. So finally, we've got two simultaneous equations, let me call them 1 and 2, that we can solve to find the magnitude of the acceleration. Now this is the usual method of doing this. They both involve t. One is minus t and the other one is plus t. So if we add these two equations together, I'm going to do equation 1 plus equation 2, we get 7g minus 3g, so 4g. T's cancel out. 7a plus 3a gives me a total of 10a, and therefore the acceleration is equal to 4g over 10. And if you wish, you can put that as a decimal 3.92 meters per second squared. So quite an involved first part of the question here. The mark allocation is as follows. There's an M1, A1 mark for doing the resolution for A, or F equals MA for particle A. Likewise M1, A1 for doing it for B. And for getting R is equal to 3g cos theta. A method mark for using F equals mu R correctly. And then as long as that had been done correctly up to that point, there's what's called a dependent method mark for getting down to this position here. So we've got the second equation now in terms of just G and A. Finally, another method mark for getting 4G equals 10A, and an A mark here for the answer 3.92. So 10 marks in total there. Well, having solved part A of the question, then we know that the acceleration is 4g over 10. So it says find the speed of B when it has moved 1 meter up the plane. So now this part B of the question, this is a kinematics question. So we can use the equation of motion v squared equals u squared plus 2as. We know that it starts from rest, so u is equal to 0. We know that the acceleration is 4g over 10. And if the distance is 1, then we have that simple equation, and that gives us a value of v is equal to 2.8 meters per second. In the final part of the question, we're asked to find the time that the particle now takes to come to rest. So what we have is that the string over here is broken. So if we now look at the forces that are acting, we have mg, the weight, and a frictional force acting down the plane, the frictional force as before, and R. So the tension has disappeared. And to start off with, it's moving with a velocity now of 2.8 meters per second. So we can call that velocity that we found in part B the initial velocity in this part of the question. So in part C, we can say that the force acting down the plane, so we've got F and mg sine theta are the forces acting down the plane, and they will give us a value of mass multiplied by acceleration. So that's just F equals ma. These are acting down the plane, so if I'm making my positive direction up the plane, I've got minus F plus mg sine theta is equal to ma. Now you may not realize, but we actually calculated this bracket earlier on, because this F is 2g multiplied by R, so it was 12 over 13, and 3g is the mass, 3g, and sine 13 was 5 over 12. I beg your pardon, 5 over 13. And that was equal to 3a. Now this bracket we calculated earlier, and of course it was equal to 3g. So we have that minus 3g is equal to 3a. So that tells us that the acceleration in this part of the question is just going to be minus g. In other words, it's decelerating with a magnitude of 9.8 meters per second squared. So we've got the value of u, we've got the value of a, and we want to know the time that it comes to rest. So at what time does v be equal to 0? So in this part of the question, v equals u plus at. We know that 0 is equal to u, which is 2.8, minus 9.8t, because the acceleration is negative g, and that turns out to give us t is equal to 2/7, if you work it out as a decimal, 2/7 of a second between the string breaking and the particle coming to rest. There were 2 marks in part B, an M1 and A1 mark in part B of the question, and then in the final part of the question an M1 A1 mark for correctly getting the equation F equals ma and then finding that the acceleration was negative g, and another one of these dependent marks, so a DM method mark. So as long as you've done it correctly up to this point, you can get a further method mark followed by an A mark. So 4 marks for that part of the question. That completes the solution to this question. Solutions to other questions can be found at www.furthermaths.org.uk.